Good afternoon and welcome to Pentair's Friday afternoon water break. Um, for the guys on the East Coast, thank you for wrapping up your afternoon with us a little bit here. And for the guys on the West Coast, thank you for plugging in some time on your lunch break for a water break with us. And today's topic is colored waters. And, being in this industry in a couple different wearing a different hats, so to speak. This is a kind of a complaint you get from customers that is a kettle of fish to open. It's sort of a catch-all for a bunch of different problems. So what do we do when we get this call? How do we evaluate? How do we break this down into something that's going to be a cost-effective treatment solution to the problem? So we're going to take a look at the sources of colored water in our world, which is going to be well water and municipal waters. Complications with with this sort of discussion, and field qualitative tests, things you can do in the field to ascertain for yourself where the problem is coming from. Maybe not dialing into exactly what the chemistry is going on in some of these cases, but understanding what methods you need to apply from that. So let's go ahead and get started. So what are the principal causes of colored water in our treatment world? Dissolved ions offer a lot of the more unusual colors that we will see in water chemistries that we deal with, from blues of coppers to browns and blacks of iron and manganese dissolved in water. And if you run into some more unusual well waters, there may be yellows, maybe even some pinks. And if you get into that environment, you're going to be submitting a water analysis you want to analyze in the first place there. And the other category is particulate, visible, and even colloidal. Visible is anything that's larger than 40 micron. But if we get enough small stuff, smaller than that in the water column, we can see that. And even as fine as colloidal particulate. Colloidal particulate, you want to kind of visualize it as dust in the water. This is particulate that's so light that it's kind of suspended in the water between the water molecules, and it's kind of stuck there. It's not heavy enough to work its way down to the bottom of the glass or the sample. So it's super, super fine stuff, and it's usually below 1 micron. So understand the difference between which one is your problem. And colors can come from anions and cations. One of the common anions with color that you may deal with are tannins. They tend to be a collection of different acids that you're looking at in the water, but those are negatively charged organic anions. So determining the cause of that color in the field, really the best solution for dealing with colored waters is getting a full lab analysis. I know that's not always doable, but that's the best one because it's going to give you the wealth of information to decide if you have a single root cause of your color or if it's a combination of things between turbidity and dissolved ions, or it's predominantly one or the other, so you can develop a treatment train. So it provides the vast amount of information you need to provide a solution. And hopefully your test will include turbidity and turbidity after acidification. This is one that'll help you separate the two. Why? That turbidity after acidification is going to dissolve any of that particulate that's related to mineral salts falling out of water, oxides like iron oxide. And any color left after doing that, that color left is going to be organics in the water. So that's going to let you know what direction you need to treat, whether it's ion exchange or carbon removal for that color that's left. And typically you are going to see more ionic color from lower pH waters. The more acidic the water is, the more likely you are to see metals dissolved in it. And this is an issue that may come up for you in something like short-term rental properties with copper plumbing. Um, we soften water to prevent scale buildup. But soft waters that sit a long time in copper plumbing will dissolve some copper. And this can be quite aggressive depending on how long that water sits. So it's a good idea to flush pipes rather than necessarily treat in those situations, right? But understanding that dynamic. If you're going to have properties that sit for a long time with softened water in them, you're going to want to flush those lines before use. And then you may have corrosion in the water just strictly from water chemistry, whether it's low pH, high amounts of dissolved gases in the water, whether that's CO2 or dissolved oxygen. You may have electrolysis, and electrolysis may come from infrastructure issues like poor grounding or stray voltage from an electrical system, no matter where in the house. If that's getting to your water supply, that can drive corrosion and some chemistries there. And people using water faster than their plumbing allows. At 7 feet per second, you'll hear a hum in the plumbing as water's going through it because it's going through so fast. This is physical erosion, and you will see blue water in the case of copper plumbing in those cases. So dissolved ions may be removed with ion exchange processes, whether they're anions or cations. So you can use backwashing systems and regenerative systems here to remove dissolved color. Now, how do you determine turbidity in the field? Well, you can invest in a turbidimeter if it's really in your wheelhouse. That's one of these devices up here. There is a Lamont chemical turbidity test that suspends particulate out, and you can judge it from a color indicator, or there's something like this in the field photometer that, besides doing chemistry, will take turbidity units in the field. And this is a visual representation of what turbidity looks like visually at different units. It's interesting to note that the federal standard is less than 5 NTUs for water. And in our commercial side of the business, anything over 0.3 NTUs, we like to specify pre-filtration in commercial applications. So what is turbidity? Well, turbidity is a scientific method that really just tells us how dirty the water is by shooting a beam of light through it. We shoot a beam of light through it, it hits a bunch of stuff and doesn't pass through. That water's really dirty. So it's a very simple qualitative test. Yes or no. How dirty is it? It's really bad or it's not so bad. It tells us nothing about the size of the particles that are in the water. Okay. But if the test turbidity after acidification, this is a test you can do in the field as well if you'd like, but this is only going to tell you if organics are present over dissolved particulate that's of a mineral nature like iron oxide. You take muriatic acid, add it dropwise into your solution until small vial, maybe 10 milliliters, something like that, and until you get a pH between 2 and 3. Any color left over is going to be color from an ionic source. So you realize that I do have organics here and I have iron particulate in the water as well. Because sometimes, oh, that's just rust. Well, there may be more there than that and may require a little different approach. So it lets you know where you're dealing with. And if you do have quite a bit of color afterwards and you don't have a full water analysis, but have a tannin test kit, take a new sample and test it for tannins, and that'll let you know exactly what you're dealing with between the three things. Now, sometimes we run across wells or water systems that have a ton of fine particulate. And a lot of times it's wells, depending on what you hit. You may hit fine sands, you may hit clays that have a very fine sticky silt to them. And we really want to identify those situations because those need special needs. There also are some municipal markets in the United States that require special filtration needs as well, like Seattle, parts of New York, where you still have wooden water mains in use. So high levels of silt in those communities in different locations. But a silt density index is what we use to understand how to set up ultrafiltration and select the right one. And this allows you to separate in the field um, your particulate classes between 5 micron and less than 1 micron, so you know what particulate you're dealing with. You separate it out, collect your next sample below that because you filtered it out over one paper, and then you filter it out over a 1 micron paper, and anything left floating is colloidal. So you can see where the distribution of your various products are, so you know what to target with your treatment. It's always a wonderful thing when it all filters out at 1 micron and above, because once you do that, get below that, we're really looking at different methods, and one of those is ultrafiltration. So the summary of the process: take a raw water sample, let it settle for 5 minutes. Okay, large scale sediment will fall out of the water column. Decant the water off the large particulate, that's pour it off in chemistry terms. Run a turbidity test on that water. How much turbidity do you have? Acidify that turbidity test and retake it. See how much color is left. Any turbidity left after that test is going to be organic in nature. Take a new raw water sample if there's organics present and test it for tannins, so you can dial in whether it is a process you want to follow in specifically tannin removal. Run the raw water filter through a 1 micron filter paper. You can buy those at Science Surplus stores and things like that. Collect the filter sample, not the solid. Any color left means you have submicron particulate. This is something you can set up and test while you do other things and let it filter down while you're talking and doing other things and see what's there. So some field processes that you can do to evaluate the waters you're on when you run into those tough colored water situations. So solutions to colored water. Tannins are an interesting category of colored water to deal with. They tend to come from shallow wells or surface water sources where you have a lot of dissolved organics. This is the stuff that makes your red wine taste bitter, right? And depending on the amount of tannin in the water and the starting water chemistry, you're going to select different methods to address this problem. And this is where a full water analysis really helps in selecting solutions for tannin colored waters. Some of them may require aggressive oxidation via chlorine, hydrogen peroxide, or ozone. And some of this may depend on what else is in the water. You may want to oxidize iron at the same time in situations like this. Other dynamics may be associated here as well. So always take that full water analysis into account. Tannins may be reduced by activated carbon or removed. Well, smaller amounts of tannins doesn't necessarily require anion exchange if the water chemistry is right. All right. Tannins may be reduced and removed by anion exchange. And typically, the higher the tannin amounts, the more you're going to look towards a solution like anion exchange. Now, quantity and raw water chemistry may require a multi-stage approach. We have run across waters where you need carbon, then anion exchange to deal with the speciations of the different tannins or different organic acids in the water. Run into that one in Florida quite a bit, where you get multiple organic acids, not just tannins, dissolved in your water. So get a full test done when dealing with dissolved chemicals in the water, not particulate. Cation colored waters are typically from low pH, so understand if you've got a low pH situation. Maybe velocity in the water. They're using too much water too quickly. This can burn right through plumbings. Have too high of a pump on the system may cause this issue as well. Very soft natural waters can cause this, or long residence time in plumbing for soft waters. That's treated soft waters can do this as well. So people who have color right after they move into a home, they just bought it. It's been sitting there 6 months. That's a flush the plumbing situation rather than treatment. For low pH, pH modification may be the solution for your color. You're going to want to do this as close to the entry to the home as possible in low pH waters to prevent pH damage to plumbing in the house. Otherwise, you have to account for that, and the homeowner needs to be aware up to this point in your home, this is exposed to this aggressive water. Air oxidation and pH modification together may be used to reduce color from metal ions. Ion exchange works well with colored waters with lower pHs because you get excellent exchange processes going on unless the pH is really low. The lowest I've seen come out of well, in my experience, is about 4 in the far northeast. Um, but you may do ion exchange and then pH modification afterwards to protect the plumbing, or pH modification before other treatment steps, depending on what's in the water. But quite often it's that pH change that will allow that color to be removed and it to be no longer a problem for the home. Um, if it's not from the water, where is it from? If you detect stray voltage, this is where having a multimeter and knowing how to use one has benefits in water treatment. Make sure your equipment's grounded. If you've installed a plastic valve head into copper plumbing and it's part of the ground system of the home, make sure you bond those copper pipes together so you have a good earth ground. That alone could create this sort of situation, and it's a good thing to check when dealing with potential corrosion issues due to electrolysis. Stray voltage issues from equipment, loose bonding lugs. We've seen this in commercial installations that just the bonding lug being loose on a system caused scale formation on RO water, less than 60 TDS. Odd things happen, right? Dissimilar metal corrosions. In older homes, you may run across things like galvanized and copper connected by someone that shouldn't have done so, right? Some of those DIY repairs that you need to pay attention to as you walk in and evaluate the plumbing system in a home or an install. Understand dissimilar metals can cause issues like going from zinc to brass is always an interesting one. If they're not using dielectric unions on the tops of water heaters and things like that, may impart color to the water after that point. So understand that those issues are there as well from a treatment standpoint we have to be aware of, because there isn't a treatment solution for it. It's a correction of an infrastructure issue. So submicron solutions in waters with colloidal particulate, advanced filtration products such as ultrafiltration may be required. We will see ultrafiltration specified on surface waters to deal with particulate and microbiologicals. You will also see it used on some well systems where you're getting colloidal clay, where it's super sticky and is gumming up the works of everything. Even super fine sands or silicates may come out of wells, or just overwhelming iron deposits in particulate from wells where it's in a broad spectrum of particle size and you're getting colloidal iron through that's staining everything and just coating everything with it. And it's really a particulate issue. You can't remove that with a water softener or an iron removal system. It's already particulate and it's blowing through your existing equipment. And in situations where it may be warm enough that you can do coagulation and flocculation in a storage tank, in an atmospheric situation, sometimes with colloidal issues, that may be the best choice, and then follow that up with a bulk backwashing sand or aluminum silicate sort of fine filtration sort of media down to 3 micron to remove that sort of coagulated and flocked material. Sometimes that's a good solution if you have a warm enough environment to do so, but that's going to add complexity because you're going to want to make sure you can keep that water biologically safe after that point. So everything has a cause and effect in choosing an option here, but sometimes this may be a better option than trying to treat it in a tank. Now, reverse osmosis for drinking water in colored waters, RO will remove the vast majority of colors from water, whether that's ionic or from particulate. But organics may follow pre-filters and membranes sooner than municipal waters. Really low pHs may be outside the operation of that membrane, so that may rule out RO for drinking water. Tannins may follow your carbon pre-filters and your membranes in these situations. And sediment and submicron particulate will be rejected, but may shorten the life of the membrane and the filters involved if there's clay sediment. So if you're aware that you're selling a RO, a drinking water RO into an untreated well water situation to manage these sorts of things, it's just a good conversation to have with your customer that these things will shorten the life of these membranes compared to other places because of the water quality. And you may want to install a pre-filter in front of it to deal with some of this stuff before it hits the RO and have a staged filtration before your RO to preserve those valuable RO cartridges. So on our next session, we'll talk about specific solutions that Pentair offers for colored waters in both residential applications and some of the things we have outside our business unit, valve and tank solutions, and advanced filtration products for larger volume applications, and some treatment train design ideas on raw water chemistry and media choice in dealing with these. We're going to talk about tannins and colloidal particulate there as well.